Okay, so shall we start the session? Okay, so let's start the session. And the first speaker is Axel Lindner, and he's going to talk about ultra-high frequency gravitational wave opportunities with ALPS II and BabyIAXO. Okay, please start.
Yeah, thank you very much. Is it working?
Now it's working.
No, it's working.
Must be slow.
Okay, now with the mic. Good, it's a little bit different talk because I don't want to repeat what you can explain much better than I do. So it's not about the physics, but a little bit of history and the opportunities which are offered by the infrastructure we've been building up at DESY. So I'm going to talk a little bit about the experimental basics, but maybe you know all this, and then focus on ALPS II and the BabyIAXO experiment, which is going to be constructed at DESY. So let me just start with a very brief reminder, so you know very well that axion is not only motivated by dark matter, but also for the CPP conservation of QCD, where I'll just try whether it works, where the coupling here to the gluon fields is the central things for the axions to explain this. Typically, experiments don't use this coupling to search for the axion, but the photon coupling, which is a model-dependent parameter, as you know, for the different models of the so-called invisible axion. And typically, experimentalists like this because we know how to generate high-intensity fields if you want to produce an axion, and we also know how to sense very weak electromagnetic fields if you want to sense an axion. So, therefore, it's basically these challenges you have to overcome. Of course, you have to generate a signal somehow in your experiment. Typically, we are using dipole magnets in the experiments I'm going to describe, where you see also what was stressed several times, that the physics of axion-photon mixing and of the Gershonstein effect is quite similar. Then we try to exploit means to amplify the signal by some resonant effects, for example. Of course, this only holds true for monochromatic axions. And we have to also discuss this. This is also, of course, a question of the monochromicity of the high-frequency gravitational waves. And then we need to measure the signal, which we have different approaches to the low-flux sensing by heterodyne sensing, which we have also heard by Aldo the talk. And we can also try to count photons with different parameters. Coherence time, as was stressed several times during this conference already, is the key parameter if you would like to use something like heterodyne detection. And in the end, I would also make a remark. Once we talk about, let's say, 1 keV energies and sensing 10 to the minus 23 watts, that's essentially a handful of photons per year. So you cannot expect to see this kind of low flux within a few seconds. And of course, if you look for transients, we have also to think of means how to position our experiment to see a transient event. And then the question is not how to really move a magnet, but how to generate a trigger to look at the correct space location in the sky. Good, in axion search, the community is following 3 different approaches. First, of course, the haloscope approach, where you look for the ambient dark matter around you in form of axions, typically microwave experiments. Then helioscopes, looking for axions being generated in the sun. And then you can try to make the axions yourself in the laboratory by this light shine through the wall effect, which is typically done with optical photons, and you can also do it with microwaves. There are different systematic uncertainties to this, which I would like to stress. So, of course, if you tune your haloscope to a specific mass, you have to believe in a certain cosmological model, just saying that at this specific mass, the axions make up a large portion of the dark matter. No one knows whether it's true, and you can pick your favorite cosmological model and then tune it to your experimental sensitivity. In helioscopes, you have to rely on some astrophysical assumptions, so it's not in all axion models the case that axion-photon conversion in vacuum is the same as in a dense plasma. And therefore, pure laboratory experiments, which are not depending and don't have similar, are not depending on such assumptions, and offer more model-independent results. Okay, at one point in time, you have to upgrade your tabletop experiments and look for really larger installations. And that's what DESY is focusing on. So therefore, the experiments I'm going to discuss a bit are here Mad Max, where the core of the experiment will be a 6 meter long, 1.2 diameter Bohr magnet providing a close to 10 Tesla dipole field. We have BabyIAXO as the prototype for the big solar telescope IAXO, and we have ALPS II, light shine through a wall, in one of the Hera tunnels. And I will focus on the following on BabyIAXO because we have some hope to start construction next year with this experiment. And ALPS II, as we have started data taking this year. So therefore, some time schedules, very rough time schedules for BabyIAXO and ALPS II might have a higher confidence level than if I talk a lot about Mad Max, where we still are in the R&D phase. Good. We have seen this on Haloscope already, the very nice presentation. I will not try to add upon what Camilla was saying. Just switch to ALPS II. Okay, ALPS II is a collaboration of these institutes, about 30 persons, lots of organizations who contributed to the funding. And I would like to highlight that the first funding was granted by the Heising-Simons Foundation, so a private foundation in the US. Maybe you know about this. This is also, I underestimated the difficulties in the beginning to get some funds because you have a nice physics idea, but typically all the funds is blocked by conventional other kind of particle physics in this case. And Heising-Simons made the breakthrough by first funding us, and then the others followed up. So this is the idea. I think you're aware of this light shine through a wall concept, where we have a laser injecting light in this string of magnets. We have this resonant amplification of the laser light, a wall, and a resonator also behind the wall here to boost the back conversion probability of axions. And this is now a sketch of the thing in the Hera tunnel. So we are talking about a 250 meter long experiment where we have built out of 12 plus 12 Hera dipole magnets, superconducting dipole magnets, which we had to straighten to make the light shine through a wall. And then we have 3 clean rooms here, where here we have the high power laser, and then we have here the clean room also with the mirrors and the wall, and here we sense then the light shining through a wall. Everything is located in the Hera Hall North area, so just close to the soccer stadium, in a very quiet environment. If there's not a match, then it's seismically very, very quiet there, which really a benefit if you want to operate these high finesse cavities. This is a view into the tunnel where you see the string of magnets, or you can at least see that there's very far away the clean room with the high power laser, and on the other side we have the clean room then with the detector. It's really straight. It's not a 90-degree experiment like LIGO, although it looks so. If you remove the wall here, then you have a glimpse into the clean room where you see the guys working there. It's really high finesse optics, and we have to avoid any dust or grease of the components. Good. I cannot go into detail, but just a glimpse on the challenges. We have the sketch here again, and we have to operate these cavities here. So basically the challenge is you have here a resonating cavity, and you would like that this light, if it's transported via axions to this cavity, is resonating here, although you cannot tune the cavity directly to this light. You have to avoid any stray light from here coming to here, because this would mimic an axion. And therefore, we have this complex scheme, which I will not explain in detail. But just again, you have here light circulating in the regeneration part at a different frequency, because you have to sense the movement of the mirrors due to seismic noise in order to compensate for this. Therefore, you cannot make the regeneration cavity really dark. And this is all this natural thing that you then here also go for heterodyne sensing, as Aldo was describing, by beating the two fields here, which in principle allows you to overcome all experimental noise limitations if you really maintain the phase of the fields constant over your measurement time. Just some numbers here. This is our baseline frequency, which is built varying because we compensate the movement of the mirrors here by varying this frequency. Then we have this frequency difference. That is, I think, 46 spectral ranges of the cavity for the signal here, for the red one. And then we need to downmix this. This we do by applying here a 2.4 Hertz shift to a simulated sine and cosine wave, and then multiply it with the signal. And we have the requirement on stabilization of 0.1 microhertz. This is a challenge we had to work on for 10 years to get this going. And starting from nothing, since about a year now, we are world record holder in operating long baseline high finesse cavities with the longest storage time ever. So at this time, it was 6.75 milliseconds. Now we are over 7 milliseconds, and we aim for 15. Good. This is one scheme. The other scheme we would like to do for ALPS II is photon counting. And the idea behind is if we sense heterodyne sensing an axion, probably no one in this room will believe us. Everyone will think, okay, you made a mistake, some stray light, some issues. And therefore, we would like to be able to switch to a very different sensing scheme, photon counting, with very different systematics, and prove that our signal is really indeed a real signal and not a fake. And the technology we have been focusing on is transition edge sensing. So we have here a little sensor cooled down to millikelvin temperatures. And if this little tungsten film, in our case, is absorbing a photon, it changes from the critical point between normal conductivity and superconductivity to some resistive behavior. And we send this by monitoring the change of a bias current. And this allows us, in the end, to measure single photons with 5% energy resolution. This is here our cryostat here. We have now a second one in operation. And you see in the end here this module. And here in these corners, and these tubes here, down there are this 25 by 25 micron large superconducting sensors. The message is now we have two methods to sense very weak signals. So heterodyne sensing is working extremely nice, I must say. So we have really good prospects to reach the shot noise limitation, which you cannot overcome easily, with integration times of larger than 10 days, because any noise is integrating out. And we have very good prospects also to maintain the coherence of signal local oscillator for heterodyne sensing for more than 10 days. In photon counting, we have achieved intrinsic background, as we call it, of less than 10 to the minus 5 counts per second. System efficiency of larger than 90%, energy resolution I mentioned already. And by chance, this gives you about the same sensitivity in signal sensing for an integration time of about 20 days. Good. But this, of course, means we can only send these very weak signals if the signal persists for 20 days. So in May, after 10 years, we were happy then to celebrate the start-up of ALPS II. This is one plot only on the sensitivity. So here, you see here the coupling to photons. You see here the mass. This is the vanilla axion models, and the shaded area is roughly the area where you could expect axion-like particles being dark matter. And the aim of ALPS is to bridge the present limits, to improve the present sensitivity of experiments by 3 orders of magnitude in coupling constant, which means signal to noise improvement by 12 orders of magnitude. And maybe also if you naively extrapolate to high-frequency gravitational wave physics, okay, you might reach 1 order of magnitude sensitivity per year. This is at least what we have been doing, based on a proposal for an experiment which is already more than 30 years old. So with the initial science run, which we are now doing, which is meant to primarily test systematics, we would like to improve the sensitivity by a factor of 30 and another roughly a factor of 30 or so. With the full upgrade then of ALPS II, which brings us into the dark matter region here, which also brings us beyond astrophysics limits. And then we would like to reach the science sensitivity in 2025. And what comes next only depends on our results. So there might be other axion searches with expanding the mass range or transition edge sensor based. We would like to go for the measuring the vacuum magnetic birefringence and, of course, high-frequency gravitational wave dedicated setups. Next is IAXO. This is a solar telescope, also run by a large collaboration, about 120 people participating. Idea again, sun emits axions. Axions move through a strong dipole magnetic field, convert to X-rays. X-rays are focused down by an X-ray telescope into a very sensitive detector. At present, the limits here in this, so the green thing is limits by astrophysics on the axion-photon coupling, where my personal judgment is that I have highlighted this here because here these limits here assume untestable for the time being magnetic field configurations. So this is taken with a grain of salt, whether this is really excluded. But if you look for the limits of the CARS experiment or from horizontal branch stars, this is more reliable, and therefore I think I kept it dark green. So this line here is given by the CARS experiment, essentially. ALPS II is a little bit more sensitive, and with BabyIAXO and IAXO, we would like to reach these sensitivities here. So improve on the coupling by a factor of 4 compared to CARS with BabyIAXO, the prototype of the full system, and then the full system could go another factor of 4 beyond. It's basically the idea. We were ready to start construction about 2 years ago, but then there was Russian invasion in the Ukraine, which stopped all collaboration with Russian partners in an instant. So the magnet plans were gone. But thanks to CERN efforts, DESY efforts, and the whole collaboration, we know now how to build the magnet again without Russian partners. And therefore, very roughly, the status is that all the structure and drive system here, which move the things, we know how to build it, and it's basically funded. All the vacuum gas system, which is there, we also have everything ready. X-ray telescopes, fine. Detectors are fine. And the magnet is still in the final phase of hitting the conceptual design report, and we hope to have the check mark here also early next year. And then we could start construction. And recently, Igor Jastorza and colleagues, Igor Jastorza, spokesperson of BabyIAXO, has gotten this very nice synergy grant, which is mainly about quantum sensing of microwave photons. So it could be also very interesting for high-frequency gravitational wave searches. And this also gave another boost to get started with BabyIAXO soon. Okay. In the end, it's lots about magnets, and therefore I took this table also from Andreas' paper, including MadMax. So it's about, there's a typo here, it's not 0.5, it's 5 centimeters, maybe. You see different things. You also have to be aware of this low frequency cutoff. Let me add now for BabyIAXO and ALPS II what we know about the sensing. This is basically the parameters which are relevant, I think, also for high-frequency gravitational wave searches. Again, I would like to remark, this here means that we have one background free count after a year. So it's not easy to sense shorter signals. Okay, and then another more general infrastructure which we are pushing in our group is what we call the DESY cryo platform. So we have here a sketch of the Hera Hall North, where the Alps is in the tunnel here, and this area will be converted into a cryo platform, and we are presently installing all the cryo infrastructure to provide these cooling powers for up to 3 different experiments. One experiment will be MadMax. Okay, to summarize, options for high-frequency gravitational wave search at DESY naturally built upon our axion infrastructure. So we have ALPS II, the long magnet string with 3 clean rooms. We have the BabyIAXO dipole on a movable platform. We have the cryo platform in the Hera Hall North. and on longer-term future, also the mad-max dipole magnet. We have also acquired new competences at DESY in the course of building ALPS II and the other things, so we now know how to operate high-precision log baseline interferometry. We know how to sense very weak signals. We have also developed new DIQ and control schemes, which I didn't explain in detail, and we have also acquired some new competences in cryogenics, how to build a cryo platform, and how to build the cryostats for BabyIAXO, mad-max, and MAGO. Time schedules are very difficult because we don't know what are the results of the axion experiments. But if I just assume for a moment that we don't find anything, so it will be boring in the end, and just another exclusion, then one could maybe think of doing dedicated high-frequency gravitational wave searches at ALPS II 2029 starting, and BabyIAXO 2031, 2032. The cryo platform will be operational, hopefully, in good 2 years from now. But again, it was stressed that axion search data can also be interpreted always as high-frequency gravitational wave search data. And Aldo proposed a new scheme now how we could maybe add upon ALPS II axion search configuration just with little things which allows to take interesting data of high-frequency gravitational waves in parallel. That's also still an option. In spite of these long lead times, I think we need to come up with plans soon if we would like to have dedicated installations. Because strategic discussions at DESY and the Helmholtz Association are starting now, and we have to bring them forward basically beginning of 25 for funding. And of course, the ALPS II story tells you you need a decade in order to build a new experiment. Thank you very much.
Okay, thank you for the nice talk. So it's time for questions. So do you have any questions?
Thank you for the talk. So you mentioned earlier that you're switching to single photon counting for ALPS II because you don't believe that the community would believe you for a signal. Is there like another reason for that? Because I would imagine if you turned the magnet off and your signal disappeared, I would find that at least a little compelling.
Yeah. We have lots of different things, but it's like, let's say, the Atlas CMS story. It came to my mind. At LHC, you have this two big, very costly apparatus, and the main purpose is to check each other. And when we started with construction of ALPS II, I became aware there's no competing experiment, nothing else. And therefore, I thought maybe we should develop two sensing schemes. Maybe the truth is more direction. It was not clear in the beginning whether one of these will ever work. And now we have two working schemes, and I can sell this now as a consistency check.
Thank you.
Maybe I have a related question to that. Which one is more? Which scheme does work more reliably right now?
I would say so. Heterodyne sensing is right on spot now, and we have not found limitations for heterodyne sensing. We try now to increase integration time to see whether we hit a flaw somewhere or instability of the phase stability. For the transition edge sensor sensing, we still have to demonstrate experimentally that we can suppress the black body radiation from the laboratory sufficiently well. We have ideas, but this has not been verified experimentally.
That's a 4 Kelvin system.
It's no, not 4 Kelvin. The lab is at room temperature, and we collect the light with a fiber from the lab, bring it down to the millikelvin cryostat, and therefore we have to have a filter mechanism in the cold. And maybe you know if you have a coated filter, put it in the cold, then the central wavelength is shifting. You have to compensate for this, and that's what we just trying out now.
So since you kind of mentioned that this is the year to come up with ideas for possible dedicated gravitational wave searches, so I remember at some point a discussion, I guess it was for the single photon counting scheme, of considering basically a a camera if you want, so a photon counter, which would also be able to cover a lower frequency range. Is that still something? Is that something that people are thinking about?
So at present, I have to say that our workforce is really severely limited, so that we have to focus on getting ALPS II going now for axions. But this would be a natural thing to do, to look for some kind of camera which then has also broad band sensitivity. We have to think on how to collect the light. You have to do some simulations, how the light is propagating in the beam tubes. And maybe you can think of a pixelized transition edge sensor system or something like this with a different coating, so you have a broadband sensitivity. I think there's many ideas one could follow, but we need people working on this.
Just let me comment a bit. This inverse Gaussian effect can happen at any frequency, and ALPS is working at 1064 nanometer, but nothing prevents you to build a sensor at different frequencies where you expect to have more stronger signals. So, for example, you can use the platform for gigahertz radiation or between gigahertz to terahertz radiation in the same way.
But you don't have the same finesse at other frequencies because your mirror coatings are at 1064.
No. I'm thinking just to remove everything what you have optical
keep
and
the tube.
keep the tube. Yeah, but the magnet is there, the infrastructure is there, so that can be used also.
But we have to be a bit careful because this waveguide effect limits us to basically above 1 terahertz.
Yes.
So we cannot go to gigahertz. This is probably, with a simple setup, not easily possible.
Let's say above gigahertz to.
Yeah.
Any other questions? Okay, so you can also ask the speaker after the next talk. So, okay, let's close this talk.